to introduce Sam Patterson. So Sam comes to us from Racine, Wisconsin, down south. Some people call it a Chicago suburb. But so I know Sam through not just my organic classes, but we had a medicinal chemistry tutorial this year, I think, and this is a great opportunity for Lawrence students to really demonstrate their independence, right? And so he had a really, really good work just digging into disease and thinking about how we plan, how we design drugs and what drugs are actually doing in the body. And so this talk about nitric oxide bioremediation is going to mix some of that sort of medicinal bioactivity stuff along with some basic chemistry of small physical chemist type molecules, like And so I think work like this is a really great example of how we can have broadly trained scientists tackle interesting problems. So, without more, give us a hand.
Hello everyone, I'm Sam Patterson, and I'm going to talk about nitric oxide bioremediation and the work I participated in over the past summer that involved this at UW-Milwaukee. So to understand the context of the issue of nitric oxide bioremediation, we need to understand the nitrogen cycle as a whole. So 78% of our atmosphere is comprised of nitrogen, and the large majority of this is in the molecule of dinitrogen. Dinitrogen is on the inert part of this slide. It is, that means it's biologically we don't use it. It is safe for us. However, 2.7 billion years ago, organisms developed the capability of what's called nitrogen fixation, which converted this to a species known as ammonia, which for certain organisms is an important, what we call food source and energy transport molecule. From here, other bacteria developed the capability of converting this to hydroxylamine, which is an intermediate that is really just used to be converted into these species over here. Nitric oxide is an important signaling pathway, signaling molecule in pathways in mammalian organisms, such as our cardiovascular system and immunal purposes. Nitrite and nitrate can essentially be seen as the equivalent of ammonia, but for plant species, and so it's an energy rich molecule for them, and all of these reactive species are also used we use to incorporate into our body to some degree. All living things have nitrogen in them, in our DNA, in our proteins, so a certain degree is there. Nitric oxide through another bacteria can be reduced down to nitrous oxide. We're going back to an inert molecule again, and then the cycle is completed back to dinitrogen. And like I stated before, a certain percentage is taken out of the nitrogen cycle and stored into biological systems, and then when we die, it is decomposed back into ammonia. So, for the 2.7 billion years that this cycle has been around, Mother Nature has done a fairly good job of maintaining a safe concentration of each of these species for the planet. However, humans have come around and we have meddled with it in certain ways. The first one is combustion processes. These are the ones occurring in your vehicles and in power plants, and they produce a ton more reactive nitrogen species. But the more important one to know is what's known as the Haberbash process. As I said before, we have N2 right here, and that is safe and biologically inert, and we depended, because it is the starting point that can be converted into reactive nitrogen species, we've relied on the organisms for a long time that were able to do this process by themselves for the growth of life on this planet. However, in 1909, we learned to do this process ourselves, and we learn to turn N2 into ammonia, and I've shown a graph on the right that predicts just how different our human population on Earth has been altered because of this. And if you look about today, we essentially doubled the population of the world because of this. And because of this fact, it's hard to argue that we could live in a world without a process that creates all these reactive nitrogen species. However, there are still consequences to our meddling. What are they? Well, let's start with reactive nitrogen species. Some of them are carcinogenic precursors. Nitrate can interact with organic molecules within your body to form nitrosamides and nitrosamines, which have a link to many different types of cancers. We have eutrophication. For those of you who don't know what eutrophication is, I have developed a little story to show you. So, let's say we have Farmer Bob, and he has his fields directly next to a large water source. For this next year, he really wants to increase his yields, so he seeds his ground with a ton of reactive nitrogen species, which, as we remember from before, is plant food. And so it works just as he intended, and he gets nice, big, strong crops this year. However, as every farmer does, he uses too much artificial fertilizer. We end up with more reactive nitrogen species than we need, and some of them are not uptaken by the plant, and they seep into our water table, and eventually they make their way into the local water source. Just as terrestrial plants really like this stuff, marine plants use this just as much. And so in the local water source, we're going to see a huge algae bloom essentially take up all possibility of any of life in this area. It sucks up all the nutrients, all the oxygen, and nothing else can live, resulting in a massive die-off. And then it dies too because it takes it up too quickly. From here, sorry, I forgot to get rid of those. That's going to be there for the rest of the slide. We also have reactive nitrogen species can form air pollutants through the process of sunlight, reactive nitrogen species, and volatile organic compounds such as methane, which we have plenty of. We can form ozone, which is the main constituent of smog. Now, high up in altitude, ozone is very important for protecting us from harmful UV radiation that could damage our DNA. However, at lower altitudes, it's simply just a greenhouse gas, and it is an air pollutant that can cause respiratory issues when breathed in. From here, we have, although not biologically harmful, we have noticed unusual increase in the concentration of nitrous oxide in our atmospheres. The cause of this we're not too sure of yet. However, it is a greenhouse gas, 300 times as powerful in the global warming potential as carbon dioxide, and so if we don't keep this in check, it could result in a much more significant problem in our future. Because of all what I just said, the nitrogen cycle research is focused around understanding the mechanisms by which either bacteria or other prokaryotes or eukaryotes go from one molecule to another and what chemically is happening there. And what I want to say now is that all these reactions here fall under the umbrella term of redox reactions. And redox reaction is a combination of reduction reactions, which is, you can think of as a reduction, where the products are gaining electrons, and oxidation reactions where products are losing electrons. And if we go pick any one molecule and go to the right following the arrows, we are getting an oxidation reaction, and if we are going to the left, we have a reduction reaction. So the work I helped with last summer looked into the claim made by another paper claiming that a bacteria had a capability of reducing nitric oxide to nitrous oxide. The aims of the research I helped participate in were, was this claim valid? And if so, by what mechanisms was this happening? And if we can understand this mechanism, it's one part of the puzzle in helping control the relative concentrations of these species and put them back into a safe ratios. Before I go into too much more detail on what that bacteria was and how that occurred, I want to talk about the molecule of interest within the bacteria that this would all be occurring at. And that would be a heme. A heme is the main biological target for nitric oxide reactions in general. What it is composed of is, while loose in definition, generally has an iron center and a porphyrin ring connected to it 4 times around its, we can think of it as the equator of this molecule, and we call these equatorial sites. And you can have either 1 or 2 molecules bound to its top and bottom sites, we call axial sites. In this example, you can see there's only one molecule bound to the bottom axial site, and it's a histidine amino acid. However, you could imagine that there could be some other molecule up here too. In the case of nitric oxide reduction with this molecule, what we'd be looking for is for one nitric oxide to come in and bind right here, and the heme is able to stabilize this molecule and keep it there long enough for another nitric oxide to come in, interact with it, and they are reduced down to nitrous oxide. So, a little more background on the protein, the bacteria. So the bacteria is known as Nitrosomis Europa, and the protein within this bacteria that is allegedly able to do this is known as cytochrome C554. So Nitrosomis Europa, or cytochrome C554, actually has 4 hemes within it. 1, 3, and 4 look like the one on the left right here, with the iron represented here. Here's a porphyrin ring. Here's the histidine from before, and 3 out of the 4 have also another histidine up here bound to the axial site. Because of this other histidine, it stabilizes these hemes much more, and these are not the hemes that allegedly nitric oxide is binding to and being reduced at. However, if we look at heme 2, we can see a different picture where there is nothing directly bound to the top axial site. However, we always see a hydrophobic pocket surrounding the axial site, which is amino acid residue from another part of the protein that is always at least blocking this site, meaning that if nitric oxide were to come in, there would be at least something sterically getting in the way from this occurring to some degree. And because of this, we started to become more skeptical of the claim that this reaction was actually occurring. But we wanted to still look into it. So because this is the point of this research is to understand what's going on mechanistically, we want to understand a little more of the chemistry of our 2 constituents that are reacting, the heme and the nitric oxide. So as I said before, Hem2 is allegedly, the one on the right, is allegedly where the reaction is occurring. But what makes Hem2 so different from Hem 1, 3, and 4? As I said, there is a histidine in the other ones blocking that axial site. However, that doesn't make it completely impossible for this reaction to occur there. But if we look at the d orbitals of iron between the two hemes, it starts to make a little more sense. And it comes down to energy and reactivity differences between the two hemes. So what I want you to get away from these slides is there are electrons here represented by arrows, and the lines that they lie on represent orbitals or areas where the electrons can lie when connected, when surrounding the iron. These are not all of the orbitals that iron has. However, these are the ones that would be reacting with nitric oxide, so these are the ones that are of concern for this reaction. The pictures to the left of the lines are the shapes of the orbitals, and the D's on the right are the names of said orbitals. And you can see that certain orbitals are higher or lower in energy, and so electrons higher up in higher up orbitals will be of higher energy, and we equate this with lower stability relative to if an electron was in a lower orbital. Along with that, we see either 0, 1, or 2 electrons on each line. There can never be more than 2 electrons in an orbital, but if there are 2, we consider them to be paired, and pairing of electrons is another thing that results in much more stability of the molecule. And so on the right we can see electrons in higher energy orbitals. We also see much more unpaired electrons, and both of these together make this a much better candidate for nitric oxide to bind to and react with. And this becomes even more true when we look at the nitric oxide molecule. Nitric oxide, when it is not bound to anything and by itself, is a radical molecule. Meaning that it has at least one unpaired electron, as you can see, represented by this electron here. And so, because of that lone pair electron and the lone pair electrons of Hem2, if both of those were to react together, resulting in a pairing of electrons, this would result in the stabilization of both of them a lot, giving more reason why the two would be good for this reaction. So when nitric oxide binds, we can think of, there's 3 different what we call resonance structures that it can look like when it's bound. And the difference between the 3 are on the right, and if you can't tell what's going on, there's simply different amount of electrons on the oxygen or the nitrogen. So where electrons lie on this complex change, and what affects that is really the local environment of this binding. So what does the rest of the protein around it look like? The difference in orbitals of these 3 resonance structures can be seen really right here by this one orbital pi 2p, and basically the 3 different structures either have 0, 1, or 2 electrons within this orbital. Whether or not it has 0, 1, or 2 electrons in this is going to affect how it binds to the iron center, which is why we care about this, because its relative binding strength can play a large part in its ability to be reduced in the first place. And so if we look at we have the electron orbitals of metal that are binding, we have the electron orbitals of nitric oxide, and how they are changed when they are bound together. And so we have always 6 electrons from iron, no matter what resonance structure we're dealing with. And we also always have 2 electrons right here from the nitric oxide. And so there's a certain orbitals are going to be filled no matter what resonance structure we have, because we will always have those electrons. However, whether we have 0, 1, or 2 electrons here, based on what structure we see, we'll see 2, 3, or 4 electrons down here, and this will have an effect on the strength of the bond between the nitric oxide and the metal. And so ideally, the more electrons we have in here, the more stable it becomes. And so in the end, we're looking for the complex that gives us the most electrons. How do we tell which one we're dealing with if it does bind? We have to look at NMR-Feldham notation for that. And when nitric oxide binds to metal, it's very hard to, the binding is so tight that it can be hard to see where electrons really lie on this complex. And so we treat it as one large molecule essentially, and give it a superscript that is the sum of the metal d electrons, which from the previous slide we learned will be 6 in our case, and the pi star electrons, which will be either 0, 1, or 2. And based on that, if we have a 6 or lower, so essentially just a 6 in our case, we will see a straight orientation when measuring the sample. And if we have 7 or greater, we will see a varying degree in the bend right here, and we can tell if it's a 7 or an 8 in our case based on the angle of this bend. So to bring us back to what we're actually doing here, we looked into the claim that this heme right here, heme 2, had the ability to have a nitric oxide bind to it, but also had the capability for that to be stably enough bound that another nitric oxide could come in, react with it, and form nitrous oxide. Did that actually occur? Well, on the left here is a time lapse of a spectrum of looking at the reaction when when a nitric oxide was introduced to the heme, and the signals 414 and 432 correlate to yes to nitric oxide binding to this metal center. That was a success. However, we've seen the signal for nitric oxide reduction, so that half of the equation is still not here. From here, we wanted to see if we could alter the conditions of our experiment to favor nitric oxide reduction in any way, and for that we looked to our K values. Oh, sorry, I forgot to mention also, we did see 7 NMR-Feldham notation complex, meaning that while we didn't get the 8, which would have been the most ideal, we did get a relatively good amount of electron donation from oxygen. And so, that being said, we looked at K values to see how we could improve our conditions. And so, what K values are basically measuring how well 2 molecules bind to each other. And so we have K on value, which would be nitric oxide's affinity to bind to heme 2. We have K off, which is its rate of dissociation from the heme. And then we have, what we're really concerned about is the K equilibrium, which is the ratio of the balance of these two to see how long it really stays on for. And this is the number that we want to compare with other hemes that bind nitric oxide to see if we're doing relatively well or not with its binding. And so, looking at other hemes found in other organisms, if we compare the values, we could do all of these are at least 1 order of magnitude larger, and so we have a lot of room for improvement on this. How can we improve this number? Well, as I talked to you about earlier on, there is this hydrophobic, there's this large pocket above the site where nitric oxide binds, and although this isn't completely bound to it and blocking the site, it's sterically getting in the way. So we figured if we could genetically modify the bacteria to alter this pocket in some way, reduce it in size, this would have an effect on the binding constant, stabilizing the nitric oxide more, and thus resulting in a higher chance of nitric oxide reduction. So what we did is we replaced the phenylalanine with an alanine, the smallest amino acid. This resulted in a 25% reduction in the pocket size and resulted in a binding constant 444 times larger. So significant improvements in the binding of nitric oxide. However, in this sample we still did not see nitrous oxide reduction, so we're still looking for that, or seeing if we can have that occur in some way. From here, I'm going to give you guys a little bit of my own speculation as to what I think could be looked into or improved to further improve the conditions of this reaction. The first being just looking at these other two amino acids and seeing, while not nearly as large as phenylalanine was, we could look into seeing if they could be reduced at all. That's just the most obvious thing to look at here. But from there, we could also look at the solubility of the pocket created by these amino acids. So as I said on one of the very first slides, this pocket is hydrophobic, it's water repellent, and so is nitric oxide. It is at least 1 order of magnitude more soluble in hydrophobic solutions than aqueous ones. And so if we can create the most hydrophobic pocket while also keeping in size steric hindrance of size, we perhaps could improve conditions. And so for that, I looked at the solubility in water of the 3 different amino acids. And I don't have alanine up here, I should have, but phenylalanine is relatively insoluble, as at least compared to the other ones, so we give this thumbs up. Proline is around, it looks like, almost 80 times the solubility of phenylalanine. While not being the worst one, we think we could do a little better. And lastly, threonine, I couldn't even find a number for how soluble it was. That's going to be the one that we really want to deal with and see if we could replace with something else. And lastly, I want to look at this little more obscure idea that I learned from hemoglobin. Hemoglobin, as you may or may not know, is the molecule within us that transports oxygen all over our body and also binds carbon dioxide to get rid of it. And whether or not it wants to bind oxygen or wants to bind carbon dioxide has to do with the pH of your blood, the acidity of your blood. And so carbon dioxide, if you stop breathing, builds up and the acidity of your blood increases. What this does is, when it gets acidic enough, it creates an environment where a proton that was once not on a certain part of a histidine in the hemoglobin is now there. This creates a salt bridge in the hemoglobin, which conformationally changes the hemoglobin, and this creates this new shape has a higher affinity for carbon dioxide. So what does this have to do with nitric oxide binding to my heme? Well, for that I wanted to look at the thermodynamic sigma trans effect of nitric oxide. When nitric oxide binds to molecules such as this one, it usually creates what is known as the thermodynamic trans effect. which is where the binding of that loosens up essentially the binding of the bottom molecule, and this essentially kind of gives a little more leeway to the molecule as a whole to move around. And what I theorize is if this proton is here, sorry, I should state first that in our paper we noticed even with nitric oxide binding to the heme, we did not see any labelization of this bind right here. And so there's something rigidly holding this molecule in place even with nitric oxide bound. And so what I theorize to look at is perhaps this proton is creating a salt bridge just as it is in hemoglobin, which is stiffening up the molecule, and if we can change the acidity conditions of our experiments, making it more basic so that this proton is in here, perhaps the labelization will occur, and thus, in the end, that would create a little more of an opening on the top for another nitrous oxide to come in and react, which is the main thing to get away from this slide. I wish I could have talked more about the research that's being done since I left, and I was told that I was going to, but unfortunately nothing really significant has occurred. They're really busy right now, but they currently are trying to use, well, I'm not going to explain what electron paramagnetic resonance or mass spectroscopy are. They're using them to look for electron locations because while I didn't specify this before, there is electrons moving around from different hemes in this reaction that we want to see exactly where they're going, and also mass spectroscopy to see what kind of reactions are occurring from point A to point B that we may not be seeing. I would like to thank Professor Andrew Pacheco, the professor that was in charge of this experiment at UW-Milwaukee, the grad student that I directly worked under, David Coulterman, Graham Sazma, David Hall, everyone in Advanced Inorganic and Chem 680 for hearing this. Some of you since the beginning of trimester 2, and giving lots of notes and pointers to make this better. And lastly, my parents for supporting me in everything I do. And also my girlfriend, because she listened to this for the last week at least once or twice a day. And, so I thank her for that.
Can you go back to your cycle slide? Have a multi-part question, but not a mean. So can you talk about if phase matters, or are these in different phases at all, or is it all in the soil, or just a little bit about like what
the combustion processes are the main concern for like air pollution. Those are the ones that are going to be in the gas phase. However, the artificial fertilizers is going to stay in the soil and in our water. That stays, I believe, in the does not become a gas, is not entering our atmosphere.
So is the N2O that's going to come out of your molecule aqueous, or is it going to eventually outgas?
I'm not sure what phase it's supposed to be in. It could. Are you wondering if it's just going to be released after we do this? Yes. So the hope is to be able to control this reaction in a place where we can have the reaction from the reduction to dinitrogen occur immediately afterwards, or we have it in a condition where it is contained.
It's a second process.
Huh? Yeah.
So this bacteria that some group found and then wrote this paper about, where did they find it? Like, where does it exist?
I think it's like all over the place because the Wikipedia page doesn't even say where it is. It's actually, it's ammonia oxidizing bacteria, so it's usually supposed to go from here to here. Another reason we were skeptical that this was supposed to occur at all. But it, they said just sewage. Hmm? What? Is it found somewhere?
Yes, it's very important in wastewater treatment.
Okay. Yeah.
So you said you're looking essentially at bond angles. Right?
Yes. Oh, for the NMR Felton?
Right, right.
Yeah.
So you say like, okay, 180 degrees tells us one thing, 120 tells us another. Is it that marked of a difference, right? So.
Well, between the straight and bent, yes, for sure. Like between, if it's 6 or 7, if it's straight or bent, we can for sure tell that. We believe actually in another experiment that was done that we may have seen 8 because we see a slightly greater bond angle, but that's something that they're not.
It seems very small.
Yeah, I forget how they did it.
Like X-ray crystallography or something like that?
Yes.
Yeah.
Actually, yes. Sorry. That,
Yeah.
I don't understand it, so I didn't explain it, but that was it.
So you said we don't know where N2O is coming from. Do you have no idea where the sources are for that?
That's something I got straight from the PI. I didn't look into myself. He said we're seeing a higher concentration than expected. We don't know why, but do we know why?
We get a lot of N2O from aircraft.
Okay. So that could be the cause then.
All right, thank you.
All right.
Speaker again.